Hello, this is Jack Jackson back again, and we're in our fourth of our series of videos leading up to the derivative and trying to understand that. So, if you remember, what we were looking at in these previous examples was this table right here of information about positions and times of a car going eastward down Interstate 40. And so we're interested in the speed that happens right at time 2. We did this a couple of ways. We did it by taking, say, the point 297 and the point 4, 230, and doing a slope there, or we can maybe do a slope from this side, or a slope here, even closer still. But we decided the best thing we could do is get it close as we could get and go from both sides, the 147 and the 159, and find that slope. So that gave us our best estimate of 56 miles per hour. That was the average speed from time 1 to time 3, and that was the best we could do with the data that we were given. However, notice that we haven't really narrowed it down too accurately yet, because even if we assume this car is speeding up the whole time, a little extra information there, the speed going on this hour was 50 miles an hour, and the speed from 2 to 3 that hour was 62 miles an hour, and if it's speeding up, the speed has to be somewhere between there, right at 2 o'clock. So our best estimate is the average of the 50 and the 62, which is 56, but we also found we could do that by just taking this point and doing the slope. Okay, well, what do we need in a way of additional information could we ask for if we wanted to find a better estimate? Well, we need more information, and where do we need that more information? We need it closer to our time of interest, closer to time 2. So, for example, what if we now measured it at closer by? In other words, basically, hey dude, let's look up more than once an hour. What if you look up every half hour and notice the time and the position? So in particular, what if we add these 2 points? Would that give us a better estimate? And yes, we can use those 2 points and give us the best estimate of the instantaneous speed right at time 2 that we could possibly get. Go ahead and figure that out yourself and come back when you're done. Press pause now. Well, hopefully all you did was just use these 2 points and do the slope, which is of course a symmetric difference quotient with h is 0.5. So it's 127 minus 69 is 112. 2.5 minus 1.5 is 1, which of course is twice what h is. That's delta. 2 times 0.5 is 1 for the denominator. That's our delta x or delta t. And our delta y, or delta p here, was 112 miles over 1 hour. That is, that's not 112 miles. It's actually 58 miles. Fix that. And so that's 58 miles per hour. Okay? And so that is our best estimate yet. And we've actually narrowed it down a little bit more. We could see, if we know it's increasing, we know the slope between those 2 points is, works out, you see the details, it works out to be 56 miles per hour. And the slope between these 2 points right here, 2 and 2.5 hours, that works out to be 60 miles per hour. So our best estimate is right exactly between those two of 58. We know it's somewhere between 56 miles per hour and 60 miles per hour, if we're assuming this is increasing speed the whole time. Then our best estimate is 58 miles per hour. So, what do we need to make the estimate even better? Well, the answer, we need to get even more information closer. What if we measured it here close at 1/10 of an hour? So actually what I've done now is I have here a table where I've looked at the the difference quotient with various values of h with the information I have in the table now. So remember, the difference quotient, we are going to use this point at 297. So the f of a is 2, f of a is 97. So notice the difference quotient is f of a plus h minus f of a over h. The f of a is 97 every time. So look, every one of these I'm using a difference quotient. So that 97 is not changing. And I'm going to look at different h values. So if h is 2, I'm talking about the point from 297 to 4230. So the y, or f of a, is 230. 230 minus the 97, divide by the h of 2. 2, of course, is 4 minus 2. And that works out to be 66.5 miles per hour. I think we did that estimate earlier. Then if we do h is 1, we're talking about adding 1 to 2, so that's going to the point x is 3, or t is 3. And we see its y, which is 159, so it's 159 minus 97 over 1, 62 miles per hour. And then if we could do 0.5, in our table we're looking at going from 297 to 2.5, 127. So work that out in the formula here. That's 60 miles per hour. Coming in even closer still, we could look at what happens at these 2 points right here. Again, we're keeping our point 297 fixed if we were doing a standard difference quotient. Now our new point is 102.9 for the y. Our h is now 0.1, and so that works out to be 59 miles per hour. But we don't always have to let h be positive. We could also do difference quotients where h is negative. So we could use this point over here at 0.7 and the point, of course, our fixed point at 297, and that is an h of negative 2. So notice this 97 is always the second one in the top. So 7 minus 97 over negative 2, that's two negatives, but it still cancels out to be a positive speed of 45 miles per hour. That's your average speed from time 0 to 2. We could do the average speed from 1 to 2 using those 2 points. That's with an h of negative 1, going backwards 1 hour from t equals 2, and that works out to be 50 miles an hour. Similarly, we can use the next 2 points there with an h of negative 0.5. That uses 2 plus a negative 0.5 is 1.5, so we're using this point. So now we're using the 69 and an h of negative 0.5. And finally, an h, or delta x, of negative 0.1 is going to get us to this point here. And so using that, we get the value there. So notice what's happening is these are coming in closer and closer, and these are decreasing here, and these are increasing closer and closer to, we're narrowing the actual interval down, if it's increasing the whole time, to between here and here. Whereas we started between these two values up here, then we said it was between these two, and then between these two, and they're getting closer and closer to what we're looking for. We could also do the same thing with the symmetric difference quotients, starting with using h is 2, so we're using this point here and this point here, 2 to the right and 2 to the left. Do the slope. H is 1, we're going from here to here, doing that slope. H is 0.5, we go half to the left, to right, and half to the left. Do those 2 points to find the slope. H is 0.1, we go half to the left and half to the right. Use those two and find the slope, and here the details are worked out for that. And notice in all these cases they're getting closer and closer to something that we're looking for, which is the instantaneous rate of change. Important question. What important calculus concept are we talking about here? We're letting the h get closer and closer to what? To 0. And we're seeing what the difference quotient, or the symmetric difference quotient, is getting closer and closer to. Closer and closer to? That's the limit. So notice up until this point, up until anything above question 12, okay, is actually pre-calculus material. Okay? It's dealing with slopes. In fact, it's really nothing more than basically Algebra 1 when you first learn slopes. Okay? But once we apply the limit, now it's calculus. So specifically, what limit are we looking at? Okay? Well, we're letting delta t approaches 0, okay, or call it h, of that difference quotient. Okay? h is delta x or delta t. Okay. That is what's happening here. So if we just do it in the generic formula, we take our difference quotient, which is f of a plus h minus f of a over h. That's the difference quotient. We take the limit as h goes to 0. That is what we call the derivative. We do f of a plus h minus f of a minus h over 2h. Without the limit, that's called the symmetric difference quotient. Take the limit as h goes to 0, and that is also the same limit. Another way to write the difference quotient was, if we just call the point a plus h, just call it t, then we're looking at the point a f of a as our point of interest. Our nearby point is t f of t. And so the slope then is f of t minus f of a over t minus a. This time we're thinking of the limit as the t is changing, so t is approaching a. Turns out this first limit here and this last one here, the first and third limits, are exactly the same. They mean exactly the same. It's just two different ways of writing it. This other limit is the same as well when all these limits exist. However, we have to be a little careful. Notice the difference quotient limit requires that f of a exist. And so it turns out if f of a does not exist, or f of a exists but there's also a hole in the graph, so we have a discontinuity there. So in fact, any kind of discontinuity, and this limit here for the difference quotient, take the limit, that's not going to exist. But it is possible if you have a limit of the function, you have a hole in the graph, this limit right here for the difference quotient might actually exist. Without the limit for the symmetric difference quotient might exist without the one for the limit of the difference quotient exists. In other words, the second limit may exist sometimes where the first one doesn't. In that case, we don't want the derivative to be defined. Okay? But if both these limits exist, then they will always be the same thing. So, we're actually going to define the derivative this way. The definition of the derivative is an algebraic kind of thing here. Of a function f at a point x equals a is defined to be equal to, we use the notation f prime of a. It's defined to be equal to, colon equals means defined to be equal to. The limit as h approaches 0 of f of a plus h minus f of a over h. In other words, you take the standard way of writing the difference quotient, take the limit as h goes to 0 of that, and that's the definition of, the formal definition of the derivative. Okay? Now, another reason why it's useful to use the limit here on the left, the difference quotient, rather than the symmetric difference quotient, it's kind of more useful too, because notice there are two things here that are changing, but the f of a stays fixed. Over here you got all three of these parts are changing. Makes this one a little bit easier to work with in formulas and so forth, in terms of, especially in proofs and things. But the main reason why we choose this is we want, if the function's undefined, we want the derivative to be undefined as well. How does this play out graphically? Well, remember in our picture here, this has the orange is the slope, is the secant line that goes through the two nearby points, and so the slope of that orange line is the symmetric difference quotient. The green one with the same h there goes through these 2 points, and that is also a secant line, and its slope is the derivative, is the difference quotient. So the green slope is the slope of the green line is the difference quotient. The slope of the orange line is the symmetric difference quotient, and we'll see that they're approaching the slope of this pink tangent line. So the slope of that tangent line is the derivative. Now we can see this, we'll see this in the next video a little bit better when we look at this dynamically, but here's a series of pictures, static pictures, and here it is with a larger h, and you can see these three lines have different slopes, although you will see that the slope of the orange one's closer to the slope of the pink than the green is. But then as we let h get smaller, this green point comes in closer, so does the orange point comes in closer, the blue point's fixed, and now we got three more of these two lines here are getting closer to that pink line. And as we come in closer and closer and closer still, so as h gets smaller and smaller and smaller, the secant lines, both the green one from the difference quotient and the orange one from the symmetric difference quotient, are getting closer to that tangent line. So the derivative then can be interpreted as the slope of the tangent line. So we can think of that as the slope of the curve at a single point. Now wait a minute. That makes nonsense. If it's pre-calculus, okay, if we only have pre-calculus, the slope requires 2 points to make sense. In fact, those 2 points have to have different x-coordinates, or the slope is not even defined. Doesn't even make any sense. But with calculus now, we can apply this limit concept to the difference quotient, or the symmetric difference quotient for that matter, and now we have a slope of a tangent line, which gives us a meaning for the slope at a single point on the curve. Kind of a cool new concept. Okay? The next 2 videos will use the GeoGebra sketch that I used to get those static pictures up above. You'll see me manipulate these things dynamically, and we'll get a better visual of what's happening. So we'll focus in on the visuals a little bit more and look at what we see dynamically.